Okay, so let's get started. First of all, as a reminder, the midterm, right? We're having it on Wednesday to Thursday. So it'll be released Wednesday morning, and you have Thursday until midnight anything. We'll cover up to basically the Y matrix formulation, right? So cover up to something like, I is Y times B. So since this is a take-home one, so I won't be around, all the time to answer questions. So I guess we'll have several office hours, right, to answer questions. And if you have other things, you can email me or the TA. So Trisha will have her normal office hour on Wednesday. And I can add an office hour on Wednesday and Thursday. So any time preference for the office hour? So I plan to add 1 hour on Wednesday, 1 hour on Thursday. To answer questions. So instead of having everybody email and do things like that. So any time you guys have in mind? No, so normal class time maybe a little bit too early, right? So I plan to, post the exam at 9:30. So it'll be better you have some time to look at it rather than directly just, go ask questions at that time. Okay, so let's do it, I guess. One day is before noon, the other is in the afternoon. So how about we do one, say, Wednesday at 11 a.m., right? So for the people who want to start early, that you can have a chance to look at the exam and get it over with. And then do Thursday in the afternoon. What time is Thursday afternoon? Say Thursday at 2. Does that work for people? Is there anyone who cannot make either of them? Okay, so the plan, so I'll have office hours. 11 to 12, then Thursday 2 to 3. Okay, does that work for everyone? Okay, so let's go with these, right? So I'll have office hours. You can use the normal link for my office hours. If you have questions, right? You can always email me if you have questions, right? Feel free to email. Just, take me, I may not get back to you right away, right? Right, so again, the midterm will not be overly long, right? It's not, a midterm that'll take you actually 2 days to do it. Right? Just a little bit easier for timing wise, do it this way. Okay. Any other questions about midterm? Other issues? Okay, all right. So yeah, so you get this one Wednesday morning, and you can have a look, right? So start. All right, so let's go on from last time. So recap of last time. Basically, last time we covered how to solve nonlinear equations, right? Of the form, let's say, a 2-variable nonlinear equation, xy equals to 0, gxy equals to 0. Right? So we want to solve a system of nonlinear equation like this. Okay. And the idea is, solving a system of nonlinear equations is really difficult. So it's much easier to solve a system of linear equations. And to do that, we'll basically use Taylor series. Right? So we keep using Taylor series expansion until we get a point, until hopefully we converge to a solution. Oops. Right, so if you look at the 2-variable case, if we do the Taylor series expansion, so we always, for Newton-Raphson, will guess x0 and y0. Okay, so we always guess some starting point. Then we can do a Taylor series expansion because what we have is, so written this in a vector notation, df, dx, df, dy, x minus x0, y minus y0, plus some higher order terms, right? So we keep the linear term, we ignore the higher order term, gx0, y0, dg dx, dg dy. So we ignore the higher order terms, we get a linear system of equations. Then we basically solve right, so if you form the Jacobians, so we have f and g plus a Jacobian matrix times x minus x0, y minus y0, 0. We're going to solve for xy. Okay. And we keep going with this process, right? So this is the basics of the Newton-Raphson method. Apply to two variables, be similarly if you apply to other variables. Okay. So this class, we're basically going to see some examples of this. We're going to look at some examples. And we're going to look at the particular Jacobian matrix of a power flow equation. Okay, so there's not much, I guess, more theory to say about this. It's just, the main thing is to define this Jacobian matrix J. Right, so the main thing for Newton-Raphson is, can you find this Jacobian? And can you solve the linear equation associated with the Jacobian? Okay. If you can do that, we can iterate. And hopefully we'll converge to the right solution. Right, so let's look at example. Okay, let's look at this example. So this example will have a system of nonlinear equations because of x times y. Okay, so let's look at what happens when we have this nonlinear system and we're looking at x times y. So if you recall, in our iterative solution, right? What we have is basically what we want is we want to solve. Okay, we want to solve f of xy, g of xy. Let's say we're starting from 0, plus j, this Jacobian j, times delta x delta y equal to 0. The x1 y1 equals to x0 y0 plus delta x. Right, so our goal is basically to solve delta x delta y, then form the next iterate. So everything here basically comes down to, can you compute the Jacobian matrix? Can we compute the Jacobian matrix? So we can, then we can solve it. So the Jacobian matrix is x dy, dg dx, g dy. So what is this Jacobian matrix for this specific example? Let's say for f, what is the partial derivative of f with respect to x?
One,
right? So 1, dx is 1, df dy is also 1, right? So it's important to remember how to do partial derivatives, right? You'll be seeing that. Then what is dg dx? What is dg dx? Y, right? So if you look at g, right? So g is xy minus 50. Okay? So the 50 doesn't matter for the partial derivative calculation. So dg dx equals to y, dg dy equals to x. Okay, so this is yx, right? So this is our Jacobian, right? This is our Jacobian. And our goal is to basically work with Jacobian matrix. Now, luckily, this is a 2x2 matrix, right? So 2x2 matrix turns out to be easy to invert, right? So if you look at this equation, what we want is we have delta x, delta y, minus J inverse fxy, gxy. Right, so at any, say, case iteration, we'll basically need to do this multiplication. And since this is a 2x2 system, we can just invert, right? It's easier to just invert J and keep doing this multiplication. Okay? Anybody remember how to invert this matrix? What is J inverse? If J is 1, 1, yx. Anybody remember the inverse formula?
Matlab.
MATLAB. So you can use Matlab. The tricky thing with Matlab is when you do symbolic manipulations, you need to be careful when you're doing symbolic manipulation. Here, since y and x are still variables, if you directly go inverted, if you have the symbolic language toolbox, that might work. If you don't, that's tricky. Okay, so in this case, we'll just invert it by hand. If you're going to look at a bigger system and you need to solve this iteratively, then make sure you can do the inverse correctly. Okay? Make sure that the way you can do inverse correctly. So for us, for this, so let's look at how do you invert J, right? So remember, for a matrix A, B, C, D, the 2x2 inverse is actually useful to know, right? So 3x3 inverse, there is a closed form formula, but it's not very useful. 2x2 is actually quite useful. First formula to know. So just a reminder, this is AD minus BC, right? So this determinant, and this is DA minus B minus C. So this is just a formula you can check. You can multiply and check. This is correct. So this is our 2x2 inverse. So we can write this, right? So we can find J inverse using this formula. So J inverse is 1 over x minus y, right? You swap the location of x and y. 1 is minus 1 minus y. Okay, so this happens to be the matrix inverse formula. So if you look at this formula, so the reason is sometimes it's important to know at least a little bit about where the formula comes from is when do you run into problems? We want to use J inverse. Right? When do you run into problems, right? So this is the inverse formula for the inverse. And basically we're gonna just keep multiplying it, right? So you run into problems when the matrix is non-invertible or singular, or in this case, when x is close to y, J inverse is a yield condition. So this means, right? So the determinant equals 0, so all these are the same things. So this means that when the determinant is close to being 0, since you're dividing by the determinant, you're always dividing by the determinant, this is a bad matrix to work with. So this tells you, for example, this guess is probably fine. This guess is probably fine. However, if you guess something like, when you guess x0 and y0 being the same number, this iteration wouldn't even start. Okay, so what this tells you is when you compute the determinant, you should basically, your guess should avoid the case when determinant is very small. Okay, so that's why it's useful to know a little bit the math behind this, rather than just the plug into Matlab and let Matlab computing inverse for you, right? Because, right, so here, remember our guess, x0 equal to 4, y0 equal to 9. This is probably okay. if we guessed x0 equal to 1, y0 equal to 1, what happens? As you plug this into Matlab, it wouldn't even start. Okay, we'll just give you an AM basically. We want to use this, right? So this is a bad guess. Okay, this is a bad guess, right? So there is a good reason to look at how well you're guessing at this. So normally the rule is to guess, use a starting point when the determinant is fairly well behaved, fairly big, right? At least compute the determinant of the Jacobian matrix and don't use a guess when the determinant is close to 0. Right? So other things we don't know what happens once they're running it, but at least in the first step, right? Don't get into a bad situation. Okay, so this is where knowing at least in principle how inverses are computed is helpful, right? Since determinant is involved, don't use a bad guess, right? But typically be very careful when you use a guess that everything starts at 0. Okay, that's normally not a great guess to use. Okay, and something to be careful with. But in this case, since we have the Jacobian matrix, let's look at if we're going to run Newton-Raphson, what happens? Okay, let's see what happens in this case, right? So our J at the x0, y0, you plug in the numbers into this J. So here x0 equals 4, y0 equals 9, 1, 1, 9, 4. J inverse, you can either invert this matrix in whatever you say computer or plug into the formula we had, but what we get is minus 0.8, minus 0.2, 1.8, 0.2. Okay, so this is our J inverse. And then we do the calculation, we get delta x, delta y as minus J inverse f at x0, y0. So this is minus 0.8, 0.2, 1.8 minus 0.2, minus 2, minus 14, 1.2, 0.8. Okay. So we basically get this as the delta x. So we have delta x1, y1 as x0, y0 plus delta x, delta y. Here we get this as, I'm missing a minus sign somewhere. No, it's good. 5.2, 9.8. Okay, so this is our first iteration, right? First iteration. Then we can do the second iteration. Okay, so I won't write this out anymore, but it's the same idea. Okay, so you compute the, basically you evaluate the Jacobian, you do the inverse, you multiply, and you add, you update your solution. Okay, so you can keep updating your solution. And here you get 5 and 10. Okay, you get 5 and 10. So this is already pretty good. You can plug it back into this equation and check the solution as, both equations are equal to 0. And if you do the fourth iteration, this is what the algorithm will tell you, that if you keep going, this will be stop because we already found the solution. Okay. So any question with this process? It's basically a fairly mechanical process. It's quite a mechanical process. Any questions? So you'll be doing this programming quite a bit, actually. So from the next homework onwards, you'll be writing a lot of Newton-Raphson. You'll be basically writing this loop. Okay. So the homeworks will be trend towards more programming oriented, because none of this you can do by hand. Right? It doesn't make sense to ask you to run a program, then just copy down the numbers, in a large matrix. Right? So you'll be doing this kind of programming. You'll be writing a matrix. You'll be inverting matrices. You'll be solving linear equations. You'll be doing all this kind of thing. Okay. So this example is basically designed. So in 3 iterations, you get the exact solution. Okay, you can, x plus y is 15, x times y is 50. So this is designed to be that way. But in practice, you won't exactly get a solution to the equation. Okay, you won't find the exact solution when both are 0 to the 20th decimal place. Right, this won't happen. So in practice, what do you think the stopping criterion is? Right, so in practice, how will you stop Newton-Raphson? Right, so you're programming this using a loop that's running inside a loop. So when do you stop?
When the change is below a certain threshold, maybe?
For Newton-Raphson, that's actually not how we do it. So normally for other method, you detect the change. For Newton-Raphson, there's two good things. One is you know the equation you want to be 0, right? So normally there's a two stopping criteria. You stop if basically f of xk or g, let's say both of them, right? You stop if this norm is less than some epsilon, right? They're fairly close to 0. At every iteration, you evaluate how good your solution is. And if the norm is for this vector is very small, inside you're close to 0, then you can stop. Okay, so this is success. You can stop if max iteration is reached, right? So you can stop if I say I have a limit of 1,000 iterations. After 1,000 iterations, I did not successfully stop. Then here is actually failure. So the tricky thing again with Newton-Raphson, and you'll see this once you start doing more programming, is if it converges, it converges actually quite quickly. Newton-Raphson is one of the faster converging algorithms out there. It converges, very quickly in a few steps. The issue is if it fails to converge, let's say you did 1,000 iterations and still the answer is not close to 0. The difficulty there is you don't know whether the problem is infeasible, means there's no solution, right? Solving the system of linear equations, or you start with a bad initial guess. Because normally for Newton-Raphson, as you don't succeed after let's say some max iteration, you normally try at another few starting points. Okay? You try at some different starting points. Okay? So it's not. So the algorithm is not as good as we want, right? It's not if if it will either converge to a solution or declare infeasibility of the problem. It doesn't do that. This is only if it converges, it converges. But it doesn't converge, we actually don't know exactly what happened, okay, in the steps. Okay. Right. So any questions about this example? Okay, so again, so this is just a summary of the Newton-Raphson method. Again, once you get a hang of this, it's fairly mechanical. It's quite mechanical procedure. Okay. The tricky thing with using Newton-Raphson in practice is actually knowing what to do when it doesn't converge. That's where the art comes in. If it converges, it converges. Right? So there's not much to say. If it converges, if it doesn't converge, then it's a lot of debugging going on. Okay? Right. So now then, this is sort of the generic story of Newton-Raphson. So now let's apply it to power flow equations. Okay, let's apply it to power flow. Okay, as a reminder, this is our power flow equation. Okay. So we're, when you apply the power flow, what happens is basically we need to do a lot of derivatives. Okay, so you look at this. Basically, when the application to power flow comes down to doing derivatives of this form. Okay, we'll be doing a lot of derivatives because that's where the Jacobian matrix is a partial derivative of functions with respect to the variables. So we'll be doing a bunch of partial derivatives. This is basically a set, way the power flow Jacobian looks like. Okay, there's, once you do a lot of them, you sort of recognize what they look like. And the tricky thing was applying Newton-Raphson to power flow. You need to be careful when you're doing this partial derivatives. There's a lot of sine and cosine. There's a lot of voltages apply each other. Okay, so none of these derivatives is, they're all simple in some sense, but they're sort of very tedious. Okay, the derivative gets tedious. So when you write your own code, you want to make sure you can do this derivative correctly. And since whatever language you're using is probably not good enough to do symbolic partial derivatives for a large nonlinear systems, right? So you need to do this partial derivatives on your own, then code these partial derivatives into the program you're using. Okay? I don't recommend going to finding a symbolic package and using to do partial derivatives. That typically doesn't work when the size of the system gets large. Okay, by large, it means more than 3. Okay, so symbolic partial derivatives normally doesn't work for power systems. And so here, what we're gonna do, I'm gonna work through this partial derivative so you see it at least once. Then when you do your own homework, let's say you have a 3-bus, you know how to program this partial derivatives. Okay, but that's our goal. We're gonna look at all these. All right, so if you look at the power flow equation, the first step is to move the injections to one side. Okay, so move the injections to one side of the equations because we want something equal to 0. Okay, so remember Newton-Raphson solves a nonlinear equation. Right, so remember Newton-Raphson solves something like fx equal to 0. So the first step is to move the injection, P and Q injections over to the left-hand side. So we have an equation equal to 0. Okay, that's the first thing we do. Then we're going to call the P equations Pi. So this is the so-called mismatched equation at node I for P and Q. Okay, so this is our notation we'll use. Right, so remember we have the F equals to 0, G equals to 0. So here we have P equals to 0, Q equals to 0. And the variables are theta and V. Okay, so the theta are the angles, V are the voltage magnitudes. Okay, so let's work through this 2-bus example. Okay, let's work through this 2-bus example. Remember, so this is our 2-bus example. Bus 1 is a generator bus. It's also the slack bus. So in bus 1, we're given voltage is at 1 per unit, angle is 0. At bus 2, we have the load, okay, minus 0.5. Again, remember, by our convention, a minus sign on the power injection means you're consuming power. That means you're consuming power. We have the line is given by impedance of J, 0.1, and our goal is to find the V2 and theta 2, so we can calculate P1 and Q1. Okay, so this is our goal. So here, this is a slack. This is PQ bus. Okay, this is PQ bus. Right, so in this case, again, we're not gonna write out the nonlinear equations and try to solve them, in closed form or using the quadratic formula and things like this, right? Here we're gonna use Newton-Raphson. We're gonna try using Newton-Raphson and see how this works. Okay. All right, so for this one, let's first of all find the Y matrix. Okay, so every step basically in all of this, let's find the Y matrix. And your algorithm, whatever code you write, the first step is always, let's find the Y matrix. Okay. So what is the Y matrix in this case? If X is J times 0.1 J, what is my Y matrix? So this you have to know, right? This is a part of the emitter. Right? So for example, the midterm doesn't cover the nonlinear power flow part, but does cover, can you give me the Y matrix? Okay. So for a 2 bus, this looks very mysterious to you.
I would say minus 10J.
Right, so this is minus 10J. What's this?
10J.
10J, 10J minus 10J. So this is our Y matrix. Okay, so X is J.1, Y is 1 over X minus J10. Okay. So here, this, for example, Y12 is minus little y. So it's 10J. And the diagonal is minus the sum of the off-diagonal terms, right? So this is where we get the Y matrix, okay? So for example, this is something that, should be something you can do relatively quickly, right, for the midterm. Okay, so I know that, a lot of you had, I guess a very long midterm that's still going on, right, at this point. But, so these kind of calculation, if you haven't looked at, since we had no homework last week, well, if you're going to review this kind of calculation. Look at your past homeworks, do the matrix correctly. Okay, good. You should be able to compute the Y matrix correctly. So we have the Y matrix. Okay, we have the Y matrix. So let's now write our power flow equations. Okay, so let's write our power flow equations. So here we have, two buses, right? So here we have two buses. So what we have is PK. If we write down our power flow equations, VI, GKI. Right, so these are just the generic equations we have for power flow. And we'll be started doing partial derivatives. And our J is G plus JB is J minus 10, 10, 10 minus 10. Okay. This is our equations. So let's start doing our derivatives, right? Let's look at this equation. How do we use it for the 2 bus case? Okay, for the 2 bus case. So for the 2 bus case, right, we need to a 2 bus case, K is equal to 2, right? So we look at this equations. Since we are given P and Q at bus number 2, our mismatched equations will be at bus 2. Okay, so let's plug in 2 equals to these, 2 equals K equals 2 equal into here, and look at what happens. Okay, look at what happens. So we plug this in. Let's see what equation value we have. Okay, we're going to look at P2. Okay, let's look at what happens when we use P2 here. Okay. So if you put in P2, we have V2, V1, right? Since G is 0, right? Since G is 0, we have B, B12 sine of theta 2 minus theta 1, right? This is what we have in this case. Do we have any other terms to this equation? Right, so if you look at the sum, right? So let's look at what happens to the sum again, okay? So we have a V2 square term, for example. Okay, we have a V2 square term. What happens to the V2 square term? What happened to our V2 square term? We have G22, for example, cosine theta 2 minus theta 2 plus V2 squared, B22 sine theta 2 minus theta 2. Okay, right? So if you look at this equation, remember we take K equals to 2 and we're running over the sum. Okay, so we have a sum of I equals to 1. This term comes from the fact that I equals to 1. So that's the first sum in this, the first term in the sum. This comes from the fact that we're running to x2. So when I equals to k equals to 2, we get this equation. So what happens to my second term here? What happens to this second term?
0.
0, right? Because G22 is 0, so I have a purely inductive line. This is 0 because G22 is 0. This is 0 because sine, right? This is 0 because sine, we have sine 0 is equal to 0. So all we have left over is my P2, V2, V1, V12 sine theta 2 minus theta 1. Okay, this is all the term I have left over here. Okay. So I can reduce this even more, right? For example, I can define B equals to minus 10. Okay. So here, let's B is, right, so Y equals JB. So here B equals to minus 10. So I can write P2 as minus B, V1, V2, sine of theta 2. Okay. Why? Because theta 1 is always 0. Okay. Theta 1 is always 0 by the slack bus. So if you look at the first nonlinear equation we have, is this P2 equation. Okay. This is P2 equation. Any questions with getting this P2 equation?
Nope.
Right, so if you have questions, please ask, right? So again, none of this, there's basically where you make mistakes is getting this kind of equations wrong. Because that's where most mistakes come from. Once you get the right equations, then the Newton-Raphson typically doesn't go very wrong. Because, you know, the computer is doing it for you, so. But this step is where a lot of mistakes happens, okay? And I highly suggest you do not use symbolic language. Do not use symbolic language, okay? So, okay, where did minus B come from? So here I have B1, 2, right? So you look at this, so here we have B1, 2. B1, 2, right? So B1, 2 is this term, okay? So minus B, right? So what we have here is just B1, 2 is minus B. But if you look at Y is minus JB. Then B1, 2 is minus Y. Right, so this is, so if we define B to be minus 10, this is minus B, V1, V2 sine theta 1, 2. It's just, yeah. Okay. And again, so I strongly suggest you do not use symbolic language, at least for doing this kind of derivations. Because there's a lot of 0 terms that whatever symbolic language software you use may not pick up. Okay. So in the past, people have tried using symbolic language processing toolboxes. It doesn't end up going very well. And it makes it very difficult for the TA to grade. Because people come and say, okay, this is what my symbolic language told me. And at the end, it doesn't work. So, where do you all go wrong? And that's very hard to grade. Okay, so now all of these you should do by hand. You should be able to do all this by hand. Okay. So this is our P term. And again, the reason that we don't have a V2 square term is the G is 0, right? There's no resistive part to the line. Okay, so G is 0. So similarly, if you look at the Q term, now does the Q term have a V2 squared term? Right? Let's look at what happens to Q. Okay, let's look at what happens to Q. Q is V2, V1. Okay, V2, V1. The G is 0, so let's not write G anymore. Minus B1, 2, cosine theta 2 minus theta 1. Okay, so that's the first term we have. This now has a second term. Okay, this now has a second term. Because what we have is we have plus V2 squared. So if you look at this equation, right? I'm running again, the sum is running from 1 to 2. So let's run it. Let's say when I is equal to 2, what happens? Oh, V2 squared minus B11 or B22, B22 term, this one, cosine of theta 2 minus theta 1. Okay? I have this term also. So theta 2 minus theta 2 in the Q term. This is 1. This is 1. So if you collect terms, and this is will be minus B, V2 squared, plus B, V1, V2 cosine theta 2. Okay? So this is what Q2 ends up looking like if you go through this calculation. Okay? All right, so if you just look at this P and Q equations, you may feel these are symmetric, but they're not. Okay, you really need to plug in all these numbers and see what comes out P and Q. Okay, for example, this Q term has a V2 square. Right? Q has a V2 square term, P does not. Okay, any questions? Was there a question? Somebody talk? So how come the V2 square term is gone? Okay, good question. So okay, so let's add a page and look at the V2 square. All right, so let's look at P2 again, right? So I'm gonna write out. I'm gonna write out the whole thing about P2 with these two terms. Okay, so let's write the whole thing for P2. So this is V1, V2, G12, cosine theta 2 minus theta 1, plus V1, V2, B12 sine theta 2 minus theta 1. Okay, so this is the first term, plus V2 squared, right? So if you just follow the formula, V2 squared is still here. V2 squared, G22, cosine theta 2 minus theta 2, plus V2 squared, B12 sine theta 2 minus theta 2. Okay, so we're okay up to here. Okay, so let's look at what term disappears and what term remains. Okay. First, G12 equals to 0, G22 equals to 0. Right? The line is x equals to j.1. There's no resistive term associated with it, so g's are all gone. Okay, so g's are gone. So this thing is gone. This thing is gone. Okay, so this thing too disappears. The sine of theta 2 minus theta 2, right? So if you just follow the formula, it tells you theta 2 minus theta 2, that's fine. This is sine of 0. This is always 0. Okay, so we don't need to consider this term. This thing is gone. And all I have left over is this thing. Okay, this one term. This is one term. Okay. So why is Q different? Basically, in Q, this term, we have a cosine theta 2 minus theta 2 associated with the B term. Okay, so it doesn't disappear. Right? Cosine 0 is 1. So this thing still survives. So that's why there's an asymmetry between P and Q. Does this answer your question? Okay, good. Yeah, so again, when you write out these equations, again, be careful. Be careful. What term is 0? What term is not? And cosine 0 is 1, sine 0 is 0. So all these are basic things. But if you're doing this very quickly under a lot of pressure, there's actually, I'm fairly sure the first time all of you do this, something will go wrong. There'll be a bug somewhere. Okay, so if the first time you write your code, it doesn't work, this is the place I will check. Okay, make sure the power flow equations are all done correctly. That is our check. Okay, so, also, right, this is where kids, when you're doing homework, help out each other, right? Check each other's power flow equation derivations, check out the Jacobian. It's definitely, it's easy. Sometimes it's easier to get somebody else to look at what you have done. Right? than just sitting there and staring at the equation for 3 or 4 hours. Right? So okay, so anyways, so we have the P and Q here. All right, so this is our, so we have 2 equations, right? So you remember now we have 2 equations. Into my 2 equations. P2 is minus B, V1, V2, sine theta 2. Q2 is minus B, V2 squared plus V1, V2, cosine theta 2. Here is 2 equations, 2 unknowns, right? Because we have V1 is 1. So V1 is 1, that's something we know. So we may just well directly substitute. Okay, we may just directly substitute here in here. Okay, so we have P2 as minus B, V2 sine theta 2, Q2 is minus B, V2 squared plus B, V2 cosine theta 2. Okay, so here are really 2 equations, 2 unknowns, right? We don't know V2 theta 2. We have 2 equations because we know the load. Okay, so we're going to solve these 2 equations. Right? We use Newton-Raphson to solve these 2 equations to figure out V2 and theta 2. Okay. And so any question up to here?
So for Q, why is B with V2 squared? Shouldn't that be the B from node 2
so
to
this
node 2?
is my B term. Right, so I have a minus V2 squared cosine. Right, so you look at Q, B goes with the cosine term.
What is the, but isn't why are we using B for B12 and B22?
Oh, why are we using BU? Okay, so we're not, right? So we're not. Remember, we only have 1 line, right? We only have 1 line. Right, 1 line. So we can define a single number B, small b, because we have 1 line, and that's minus 10. So if you look at the equation, so is your question why this is a minus sign and this is also a minus sign?
No. For the first line with Q, we have a capital B12 and a capital B22.
Yeah.
Why are we using the same value for both of those?
We're not. This is B. This is minus B. So B12 is minus B22. That's why we have a minus sign here and no minus sign in the second term.
I think I'll have to look at it later.
Yeah, so we're not, right? So, okay, so let's just be sure. Let's just be sure where they come from. So actually, it's important to get this correct. Otherwise, when you're doing this derivation on your own, you have a lot of problems. So let's look at Q2. Okay, let's again look at Q2. Let's write out everything again. Okay. Well, let's follow our equations for Q2. I just blindly plug them in. Then we'll do reductions. Okay, so if you blindly plug them in, V1, V2, G12 sine theta 1 minus, sorry, 2, 1. 2, 1, theta 2 minus theta 1, minus V2, V1, B2, 1, cosine theta 2 minus theta 1. Okay, so this is just blindly plugging in, plus V2 squared, G22, sine theta 2 minus theta 2, minus V2 squared, B22 cosine theta 2 minus theta 2. So are we okay up to here?
Yes.
Okay. Then let's look at this, right? So this term goes away because G is 0, right? This term goes away because G is 0, and we're doing sine 0 equals to 0. So both of these things disappears. Okay, so we're still good now. Okay, so let's look at it. We have B, our B matrix is minus 10, 10, 10, minus 10, right? This is our B matrix. We define small b to be minus 10, okay? So here we have B21, use 10 equals to minus b, right? So this minus b and this minus sign, what we have is, so if you want to write out this even more, is minus B21, right? Minus B21. When you plug in B21 equals to minus b, you just get b, V1, V2 cosine theta 2. Right, so B22 is minus 10 equals to b, minus V2 squared, b V2 squared, minus actually just b V2 squared. Does this help?
Yes, I didn't realize that we were referring to matrix coordinates. I thought those were impedances between nodes. So
Yeah, so capital, right? So capital letters are always matrix coordinate, right? So B is a matrix, right? So G, capital G, capital B, capital Y are all matrices, right? So that's why we're referring to, right? So if you look at sort of the basic equation, these two basic equations, where G and B comes from is Y matrix is G plus JB, right? So this is all matrix coordinates. Yeah, good. Any other questions, right? So if you have questions, please ask. Please ask. Otherwise, this is 2x2 bus. This is 2 bus, right? So in the homework, eventually, as the class goes on, we'll have a 12 bus example. We'll just keep looking at. Right? So it's not more complicated than this, but you do basically repeat this calculation, many more times. Right? So if you have questions, please ask.
Professor.
Yeah.
So when we have a situation where we have more than one line here, so this one we just have one value for b is equal to negative 10, right?
Yeah.
We're going to have one matrix, still one y matrix.
One y matrix, yes.
Are we going to denote like each line? Would you normally denote each line having like a b value as well?
No, in that case we won't, because in that case we'll still just do this calculation, but we won't denote each line.
So we're just going to stick with the matrix like coordinates.
Stick with matrix. Here we use small b because I want to show the matrix with numbers.
Sure. Okay.
Just either, So in that case, you just have, just use the matrix notation, right?
That makes sense. Thanks.
Yeah. So when you write your code, you're basically just looping over the matrix coordinates, anyways. That's how you build the y matrix. Once you build the y matrix, you write the power flow equation in your own code. You just loop over the matrix coordinates together. Okay, so no more questions. Okay, so let's now take our break. Okay, so one more question. But G is 0, right? So G is a real part of the Y matrix. Here, the Y matrix is purely imaginary, so there's no G. But G is 0, yeah. So when you see a line, and the line is just purely inductive, there's no G, right? There's no G term. And often when we do a small example, either in your homework or in class, we won't have G. This just makes the equation, G just makes the equation twice as long. Right? So, and in practice, G is quite small compared to B. Okay, so that's all. Okay, so good. So let's take our break. We'll come back at 10:36. We'll finish this example with all the numbers plugging, and we'll look at what happens when you run Iterative. Okay, so let's get started, finish with this example. Okay, so basically, if you plug all the numbers into here, okay, plug all the numbers into here, and we're going to drop so we're going to drop the subscript P2 and Q2, so we don't have to write it out every time. So we're plugging all the numbers in here. What we have is we have P as a function of theta and V. This is 10 times V times sine theta plus 0.5. Q theta V. This is 10V squared minus 10 V cosine theta plus 0.5. Okay, all right, so these are our mismatched equations. Okay, mismatched equations meaning that they're basically, they exist to, right, so this is something equal to 0, this is something equal to 0. We're going to solve for these equations to get theta and V. Right, so one thing to note is that we don't use P1, Q1. Okay, so we never use P1, Q1 because remember we already have 2 equations and 2 unknowns. Okay, so P1 and Q1 are determined by the solution of the so-called implicit equations, right? They're determined by the solution of the mismatched equation. Okay, so P1, Q1 determined by, I guess, V and theta, but not a part of the solution process, okay? Of the nonlinear equations. Okay, so they're not a part of the nonlinear equations, right? So don't write too many equations to solve. Right? So I will write the same number of equations as the unknowns you have, right? So here we have so don't write P1, Q1. They don't add anything to the equation solving process. Okay, so once you get V and theta, you can figure out what P1, Q1 are. But when you're solving for the unknowns, they don't matter. Q1, Q1, they don't enter into the picture. Okay, so we're going to just ignore them, and we're going to look at the Jacobian of these power flow equations. Okay, so when we look at the Jacobians, which we'll be doing quite a bit, as a reminder, J is P d theta, dP dV, dQ d theta, dQ dV. Okay. So we're just plugging all the numbers into here. So when you take derivatives, we have 10V cosine theta. Okay, so derivative of sine is cosine. Here we have 10 sine theta. Right? V is linear. So V goes away, we take a derivative. Second derivative is 10V sine theta. Then this V is 20V minus 10 cosine theta. Okay. So this is our partial derivatives that forms a Jacobian matrix. So any question with this Jacobian matrix? Right, so just partial derivative. So one thing to note is that by convention, the ordering is theta then V. Okay, so this is a convention, right? So here there's 2 variables, theta and V. So in principle, you can, y is d theta then dV. right? In principle, you can do first take derivative with respect to voltage, then take derivative with respect to angle. However, the convention in the field is always, right? The convention here is always theta then v, right? So here, to clarify, theta is by definition theta 2, v is by definition v2, so I don't have to write out the subscript 2. Right on, yeah. Okay. So the convention is actually important. This convention is actually important. So theta goes before v. Okay, and please follow this convention. Makes grading and debugging your code very much simpler. It makes everything very much simpler. Okay. Because right, if you do, if you do dv d theta, v before theta, then is you have the opposite ordering, which will work out at the end. But the convention is so, this convention is followed everywhere. Right? When people say power flow Jacobian, it means as charge derivative with respect to theta, then v. Right? That's just when we say it just means this way, right? So then our first iteration, right, is clear. We have delta theta, delta v as minus j inverse times p q and theta 1 v1 is theta 0 v0 plus delta theta delta v. Okay, so this is our iteration. So to solve this equation, right, we have to get a start point somewhere. Okay, we have to get a starting point. So with almost always what we'll do, we'll pick a flat start. A flat start means that the voltage is 1, the angle is 0. Okay, we'll almost always pick this flat start for power flow equations. The first thing you try is a flat start. Okay. So obviously the flat start doesn't work, right? So you can evaluate the mismatched equations. There's non-zero mismatch, right? So, but it's good to use these as a starting point. Good to use this as a starting point. Right, so we use a flat start as starting point. Then you can compute the J, the Jacobian matrix associated with these, right? So remember, the Jacobian matrix is 10 times v0 cosine theta 0, 10 sine theta 0, 10 v0 sine theta 0, 20 v0 minus 10 sine cosine. Okay. You're plugging in all these numbers, you plug in v0 equals to 1, sine 0 equals to 0. What you get is 10, 0, 0, 10. Right? So this is a good starting point because this matrix, Jacobian matrix, J, is very invariable, right? So the condition is well conditioned. Basically, the determinant is fairly big. Okay? So that's a lot of times for the reason why we pick a flat start. As by doing flat start, you almost always guarantee at least the first Jacobian start up with will be a well-conditioned matrix. Right? The determinant will be far away from 0. Okay? So if you take some other random starting point, you may not have a very good Jacobian start with. But here, if you take the flat start, it's a good Jacobian. So that's what we will do.
Professor?
Yeah, go ahead.
So for the first iteration, you said that P is finally equal to 0.5 and the Q is also equal to 0.5.
Yeah.
But I mean they're both 0.
No. These are the mismatch equations. I want P and Q to be both equal to 0.
Yes.
Right. I want them to be 0. They're not. They're 0.5.
Oh, after the calculation. Okay, thank you.
Yeah, right. They're not. Right, so there's a reason why it's 0.5. It's because, so what happens in the system, right? This is a 2-bus system. Right, so this is slack. So this is always 1 angle 0. What happens if this is also 1 angle 0? If I pick my flat start, do I have any power flow? No, right? So there's 0 flow. Nothing happens in the system, right? So that's why you have a mismatch on the load, because you're not delivering any power to the load. Okay, so that's why the mismatch works out this way. But when nothing is flowing on the network, the Jacobian is a nice matrix. Okay, so Jacobian is quite nice, right? So that's why we'll pick this as a starting point. So this is obviously a bad guess, because at flat start there's no flow, and so the load is not satisfied. That's why you have a mismatch as a load. But Jacobian works out, so we'll pick this as a first starting point. Then you have your delta theta delta v minus J inverse P theta 0, V 0, Q theta 0, V 0. So this will be minus 0.05, minus 0.05. So your theta 1 V1 will be minus 0.5. Okay, so this is our first up. We do the first iteration, we get a small update. Okay, we get this small update on voltage. The angle is actually relatively larger because it's in radians. So this is our first step. Any questions about the first iteration we take? So after this, it's quite mechanical. It's quite mechanical because you plug into the power flow equation, the mismatch equations. We figure out, hey, the mismatch went down, right? Remember before the mismatch was 0.5. Now the mismatch is 0.02 and 0.03. Okay? So we reduce the mismatch, right? We want this to be 0. So we reduce the mismatch quite a bit. Right? So then let's keep going with our iterations and see what happens. Right? So we can have second iteration. You can plug this into your Jacobian. Right? So now it's, I'm not some, anyway, so some numbers in the Jacobian. Sort of some things here. You can do this again, right? So we have delta theta, delta v, J inverse, theta 1 v1, q theta 1 v1. So you do this, what we get is theta 2 v2. This is minus 0.0528, 0.9462. Okay, so this is after one more iteration. You plug in here, hey, the errors are mismatch are, pretty small here now. So often at this point, you can basically declare victory, right? So a lot of algorithms will just declare victory at this point, saying the mismatch are small enough, we can stop. Okay, so if you want to be, right, so we can just stop here, or we can do one more iteration if we really wanted to, and then we can do one more update, computing the Jacobian, doing the inverse, computing the update, and so on. And this is small update. Okay. You have a very small update here, meaning that we're close to a solution because our mismatch are quite small. Our mismatch are quite small. So here, if you look back, right, so we can basically, this is our solution. This is our solution. Well, then we can compute P1 and Q1. Okay, we can compute P1 and Q1, and we can get what is active power being generated at P1, what is active power, what is reactive power generated at Q1. Any question with this process? Right, so again, it's a very mechanical process actually. This once you get the Jacobian set up, then you just sort of crank this, just crank it through, and it works out. You'll converge super fast. The good thing with Newton-Raphson is if it converges, it will be something like this. after a few iterations, your mismatch will be, almost exactly 0, quite close to 0. So let's do a standard. Yeah, go ahead. Any question? Okay.
How determine when is the last iteration?
Oh, so you're right. So there's basically, you can look at this, right? So the mismatch is already pretty small, right? So you have some tolerance on how close to 0 your mismatch is. Right? You have some tolerance, right? So that's the tolerance you can set by yourself, right? So you have to set some tolerance. So looking at these are pretty small tolerances. So normally the ballpark number for tolerance is something like 0.1%. Okay, right? So remember, we're mostly working with per unit system now. So your tolerance will be like 0.1% of the base unit. Right? So then you can stop. Okay, so that's sort of a rule of thumb. But you can set the tolerance on your own, some not too big, right? So don't set the tolerance to be like 5%. But as long as your tolerance is, fairly small tolerance, and you stop once you reach the tolerance, that's fine. And another way you can figure out you're almost converging is when the mismatches are small, and your update has almost stopped. But at this point, you're making tiny update anyways. And since your mismatch is already quite small, then you can just stop your algorithm.
So in this example, we stop at the Z2 and the V2.
Sure, yeah. Or V3, right? So you can do one more iteration and get to V3 if you want. It's not very different than V2. Yeah, so normally you just run it into something like 0.1% tolerance, then you stop. Right? So the good thing with Newton-Raphson is if it converts, it will convert really quickly. So doing a few more iterations just to be safe doesn't hurt. Okay, so we got a solution like this. So does the solutions make sense if you just want to look at it? Right, so remember P2 and Q2 are both 0.5. Does it make sense for P1 to be also 0.5? And why is P1 equal to P2 in this case?
Oh, Professor, I think it made me think here.
Yeah, sorry, okay, go ahead.
Yeah, say the Z3 equals to the minus 0.052891. Go slides. Go a little bit down. Next slide.
Okay.
It says the Z2 equals to the minus 0.529.
Yeah, when the stop at there's the only if you don't want to keep that many significant digits, I guess we have to run it out somewhere, right?
I think that should be the Z3.
Oh, right. Okay, so this is okay. Very similar to each other, but that's fine. Yeah, it's after 3 decimal places, but that's fine. Yeah, so you look at this solution, right? So P1 is 0.5, P2 is minus 0.5. Does this make sense? Right? Because there's no losses, right, in the system. Right? The line is purely inductive, so there's no resistive loss. So all the active power generated by the generator goes to the load. Right? So this makes sense. Similarly, Q1 is a little bit more than the demand for Q2 because your line is an inductor. So inductor consumes some of the reactive power. So part of this reactive power goes into the inductive line that's consumed by the line. The rest 0.5 per unit goes to the load. Okay, so this makes sense. This is so after you solve all those power flow equations, you should at least do some sanity check like this, right? If the lines are totally lossless, then the active power generation and the demand should balance out. If the lines are a little bit lossy, then the loss should not be very large. And the loss should not be huge. Right, and the basics with the Newton-Raphson is again quite simple in this case, right? So it just basically all you do is get the Y matrix input correct, do the Jacobians, get the formula with the Jacobian correction to your code, choose a starting point, which is almost always a flat start, then just follow the procedure. Follow the procedure, and so not so once all the coding, all the hardness in coding is actually writing down the Jacobian matrix, the formula for the Jacobian matrix, so you can invert it. And that's where most of the difficulty in coding comes. Okay. And then again, right? So if we look at NBus, same thing. We have the active and reactive power mismatch. We have active power and reactive mismatch in this. Okay. So again, we set up. These are our mismatched equations, right? So these are our system of equations. And here our convention is always V1 is 1, theta 1 equals 0. So if you look at the variables, goes from theta 2 to theta n, V2 to Vn. Right? So the voltage and angle of the slack bus, as we just we already built that into these equations. Okay, so we don't need to consider the slack bus. Okay, so we set up all these equations. So we're going to assume these are the PQ buses. We're going to assume these are PQ buses to set up these equations. And then the procedure is the same, right? It's just a bigger matrix to invert. But nothing, changes if the matrix is a bigger matrix to invert. But the interesting thing is to take a look at the Jacobian. So the rest of this class will take a closer look at the Jacobian matrix. But mechanically, T bus to N bus doesn't change all that much. It's the same procedure, just a bigger matrix to work with. But it's interesting to take a look at what the Jacobian is. A little bit interesting to take a look at what the Jacobian is. Because once the system gets very large, we may start to make assumptions about the Jacobian, and it's good to take a look where the assumptions come from. Right? So if you write out the Jacobian matrix, okay. So remember what the Jacobian matrix is right. So this the first part is dp d theta. Okay, so it's the matrix version, but this is dp d theta. This is dp dv. This is dq d theta, dq dv. Okay. If we write this out, what we have is basically we want to really, write things out. Theta n, dpn, d theta 2, dpn, d theta n. Okay, so this is the P part. And you just repeat this for the Q part. So dq2 d theta 2, dqn, sorry, q2 d theta n, dq2, dqn, d theta n, d theta 2, dqn, d theta n. So as the last, you have the Q versus V part. Vn. And we will write this as J11, as block matrices G11, G12, G21, and J22. Okay. So we'll write them as block matrices, right? So, and actually, sometimes people give each sub-block a name. It turns out these block matrices have been studied actually quite closely. These are, if you go to, if you really go to a vendor that's programming path flow solvers for utilities or system operators, you'll become very, very familiar with this each submatrix, each block matrix. And these are entities. These are sort of things that are close to a lot of people's heart. They actually have their own names, which we're not going to, but they each have their own special little name, that's called. Well, we'll just look at the property of these. Okay, we'll just look at the property. So let's look at something, So let's look at something. So this Jacobian right now, let's look at the J11 term. Let's look at sort of the J11 term, what we have for our Jacobian matrix. And we'll basically look at which term is large and which term is small. Okay? So, right. So if you look at, let's skip doing the derivations. Just show you this term. Okay, let's show this to you. Okay. So if you look at this J11 term, you can. This is our mismatched equation. You can basically take partial derivatives and look at what happens to all these terms. So if you look at this term, let's just look at the off-diagonal J11 term. Okay? Let's look at this term. We have two terms. We have a G term and a B term. Which one of these is larger? Right. So let's see. If you look at these two terms, which one is larger? Is the G term larger or is this B term larger in terms of power flow Jacobian? Which do you think dominates in magnitude if you sort of compute the Jacobian and write it out? The B term, right? So the B term often dominates, right? So normally in magnitude-wise, the B term will be much, much larger than the G term. And the reason is actually twofold. The reason twofold is, right? So normally, or not normally, but most of the time in the transmission network, we have Gij sort of smaller and smaller than Bij in magnitude terms. And sine theta I minus theta j is much, much smaller than cosine theta I minus theta j. So we have these two impacts, we have these two factors. So very often what happens is the second term will be much, much larger than the first term because both G and sine tends to be small. Okay, so often, so some algorithms will just ignore Gij sine theta I minus theta j. Okay, some algorithms will just ignore this first term because saying, okay, this doesn't matter, it's too small, and we'll just take the second term to be large. Okay, so if you look at under the hood, especially of some sort of the older algorithms, basically you will just not care about the first term because it's often much, much smaller than the second term. Okay, this is what we do. If you look at the G12 term, okay. So G12, remember, sorry, J21. If you look at the J21 term, right? If you look at J21 term, as a reminder, J21 as Q versus V, Q versus theta, okay, Q versus theta, dQ d theta, right? So if you look at these two terms, what happens here is this is small, this is small. Okay, so GS tends to be small, sine of the angle tends to be small. So altogether, actually, what happens is this J21 term tends to be small. Okay, so if you look at this whole block matrix, it's basically not a very not a very large numbers in this term. Okay, so if you look at something like J11, J21, J11 tends to be much larger. The terms in J11 tends to be much larger. Okay, so although nowadays you just plug into a computer and just crank through the numbers, actually sort of some structure in this matrix. Okay, quite a bit of structure. Similarly, if you go on with this term, so if you look at J12 term as this is small, this is small. So the J12 term is small. It's quite a bit smaller. J22 term is basically you still have this sort of large term, large, and this is small. Okay, so this is sort of the 4 terms we have in our matrix. So the reason I want to go through these 4 terms is they're sort of somewhat actually sort of some interesting history on how power flow matrix is used, right? So if you look at the J matrix, okay, so let's think about the dimension of this matrix, okay? If we look at things, the J matrix, let's think about the dimension of this matrix, right? This is a roughly 2n by 2n matrix. Okay, I say n as something like a 500. So J is roughly 1,000 by 1,000 matrix. Okay, J is roughly 1,000 by 1,000. Right now, if you're telling a computer to invert 1,000 by 1,000 matrix, well, do it. Will take a little bit of time. It's not even that fast in our modern computers. It takes a while to invert this matrix. But if you tell your computer, basically, and so imagine when we're first looking at power flow. Okay, so for you guys, when do you think we first started using power flow calculations? Right? Approximately what year are we solving power flow? Is the system large? We have enough. We can collect data. We can collect P and Q. When did we solve it? Right. So this was 96 or 1970s, and this is actually, you should be proud. It's BPA, which managed the Seattle grid. Right. So sort of BPA, the system operator of Pacific Northwest, is the first system operator that started to use power flow. History-wise, if you think of now it's used all over the world. Actually, BPA, which means Seattle, we are the first one to start solving this. But in the 1960s and 1970s, you tell a computer, go invert 1,000 by 1,000 matrix every time, every loop. I want to use the Newton-Raphson. All the computer in all the world altogether were not able to do this. You can take the entire computing resource of the entire United States, will have trouble solving this Newton-Raphson for you. We asked it to invert 1,000 by 1,000 matrix every iteration. It would not happen. Okay? So it turns out power flow is actually one of the first methods where scientific computing, where using computer to solve large scale problems, coming to actually computer was used for this. This first civil application, basically, of large scale computers. And this is actually, maybe the first civil application. But even then we have problems because we cannot, right? We cannot deal with this large matrix. We have to keep it at every iteration. Now invert or solve our linear matrix equations. So what do we do, right? So how do we make this more practical? But we cannot deal with this matrix. What people figure out is following, hey, why are these sort of blocks so special to us? If you remember our discussion, this block matrix like this, we set J11 as much, much larger than J21 or J12. J22 is much, much larger than J21. Okay, so for people were doing this calculation by hand, they figure out, hey, even we have 4 blocks, they are not all symmetrical. The diagonal blocks are much larger in size than the off-diagonal blocks. So to get your computers to work, as first, we're going to kill these 2 blocks. Okay, we're going to just ignore them. They're much smaller in size, so let's not worry about it. So roughly, what people in BPA did, and a lot of people around, what they did is they said, let's ignore the off-diagonal things. We're going to make this into a block matrix, which is nice, right? Because I have the size of the matrices, which is actually very, very important when you're, that earlier on when you're doing powerful calculations. But this is not the end of the story. This is not the end of the story. Because even a 500 by 500 matrix, you ask a computer in the 1970s to invert it, no computer will do that. You run out of memory way before you did even one iteration. Okay? We run out of memory. So people say, okay, how do I make this even simpler? For example, let's look at something like J11ij. Okay? Let's go back to our J11ij and look at why this happens. So what happens is VIVJ. So if you write this out again, Jij sine theta I minus sine theta j minus Bij cosine theta I minus theta j. So we're going to make the computation much easier than before. So what happens is this is my diagonal block. Let's throw away things. Okay, I need computation to be simpler. Anytime I can throw things away, my computation is simpler. Let's kill this term. Okay, sine is typically small, g is typically small, so let's not worry about this. Okay? Then let's look at more assumptions I can make. Vi is roughly 1, Vj is roughly 1, doesn't change all that much, so let's not worry about voltage. Okay, let's just say they're all 1 when we get to this point. Now cosine theta I minus theta j, this is roughly 1. Right? The angles are separation are small, is this cosine 0 roughly 1, so that's all these are okay. So we'll actually make this following assumption. So all this thing, just Bij. Okay. After all this assumption, it's just Bij. Forget about the sine, forget about the v, forget about the cosine, this is what it is. So if you make this assumption, what happens is J is basically a constant matrix. Or just go in and make all these assumptions in J. It's just a constant matrix. The nice thing about constant matrices is something like J inverse, not exactly J inverse, but something like it, is computed offline. Okay. What you do is you basically compute it offline since it's a constant. There's nothing changing within each, right? So every time you update v and theta, you actually don't change your J matrix. So it's a constant matrix. So you do a pre-computation basically offline to get into a form that's easy for you. And then you can start doing iterations. Because every time, you just have to multiply, add a bunch of numbers. And there's a lot of tricks to add and multiply a bunch of numbers fast, using very little memory. If any of you have done, pointers in C, this is where that comes in. Okay, so you basically write your code in a very compact, efficient way, assuming J is a constant matrix. And this amazingly worked. Okay, the BPA basically figured out, hey, this thing worked. And if you look at the paper BPA published, this thing method, and people working in math like, okay, you can't do this, right? You can't just throw away things. You can't assume things are 0. You can't just make whatever assumption you want as your computer works. But at the end of the day, you show this is your code, you put it into your computer, and in practice, it works. Okay, so nowadays, when you write your code, you just type in inverse of J. But keep in mind that for this whole method to work, whole bunch of engineering went into it. Only now is the story a little bit clear why this method works, why you can just assume it's a constant matrix, why it's actually worked better a lot of times than inverting it every step or solving the linear equation every time step. But so this is a little bit history. You should feel proud, right? So BPA is the first people to do this. They really made it possible to operate large power systems. And the reason they made it possible to operate large power systems, and they figured out what to do with this Jacobian matrix. So Newton-Raphson, by the virtue of the name, was known when Newton was around. It was never used for large-scale problems because people couldn't deal with matrices. And power system turns out to be the first good application because we can make this sort of assumptions for matrices. and to make it run and to make it work actually at the end of the day. Right? So this is our, this is the sort of, the success, right? The success. Not many people know it, but if you think of computers came out of Manhattan projects, this is where the civil application of computers really took off. This is manage large-scale power systems. And that's why, a lot of first, in the 70s, computer was constructed to do this, right? So if somebody tells you, right, power engineering, all you do is, collect circuit breakers or, fix lines, tell them no, right? No, we're as equally important as Manhattan project making large-scale computer applications happen, right? Which is true, right? And BPA really made it happen for the rest of the country. They showed it's possible, and the rest of the world started using it. Right? So this class will end here. Next class will go into more depth of the power flow equation. We'll look more into the Jacobian. Basically, we're starting more. If you look at the Jacobian, you can mine a lot out of this Jacobian matrix. We'll take a closer look. But today we'll end here. We'll just know that when people first using it in the 1960s and 70s, a lot of engineering went into it. Quite a bit of engineering went into it. A reminder for midterms, the Wednesday morning release will be released. Thursday night is due. I will have 2 office hours, one on Wednesday, one on Thursday, to answer questions if you have any. Okay, so it's end of the lecture, and good luck on Wednesday for the midterm. Yeah, so Wednesday is Veterans Day, but as we decided, it's a take-home midterm. So, so you have 2 days, right? So we may just well release on Wednesday.